Here is the molecular geometry table I give to my students. We covered the first two columns in an earlier video where I explained the valence shell electron pair repulsion model, or VESPER. This gives the electron pair geometries. The electron pairs can be bonding or lone pairs. These electron pairs will determine the electron pair geometries in the second column. But the molecular geometries will be determined by the number of bonds and lone pairs on a central atom. That's right. As you can see, the electron pair geometries and the molecular geometries can be the same or different. Notice that when the central atom does not have lone pairs on it, that is to say, when all electron pairs around a central atom are bonding pairs, then the molecular geometry and electron pair geometries will be the same. Now notice that if a central atom has both bonding and lone pairs of electrons, the molecular geometry will have a different name. To illustrate this point, let's look at some common examples seen in general and organic chemistry of the tetrahedral geometries of methane, ammonia, and water. Methane is a single carbon atom with 4 hydrogen atoms around it. It has 4 bonding pairs of electrons and no lone pairs of electrons. It has both an electron pair geometry and molecular geometry of tetrahedral. Ammonia is a molecule with a central nitrogen atom, and there are 3 hydrogen atoms around it. It, however, has 3 bonding pairs of electrons and 1 lone pair of electrons, which I've included here. Its electron pair geometry is tetrahedral, like in methane, but its molecular geometry is called trigonal pyramid. Notice the bond angle is slightly sharper than in methane. This is because the lone pair of electrons atop the nitrogen atom are not bonding, so they occupy more space than a bonding pair. Finally, water contains a central oxygen atom surrounded by 2 hydrogen atoms. The oxygen atom has 2 lone pairs of electrons, which I've included here. The oxygen has 4 pairs of electrons total, giving it an electron pair geometry of tetrahedral, but 2 bonds and 2 lone pairs gives a molecular geometry of bent. The bond angle is sharper than that seen in ammonia because 2 lone pairs occupies more space, thus making a sharper bond angle. Here once again is my molecular geometry table.